I see Krishna joining as well. Hey, Krishna. Okay, so
I see.
yeah. So what where should I start? So localization per se is we start with something. We look at all the sensor data and try to figure out where we are in the map. So it's kind of like a circular definition where when you say that you are somewhere, like localization basically says you're somewhere, right? And then when you say you're somewhere, you need to know, you need to actually also define with respect to what. You can, let's say you're giving a GPS coordinates. So GPS coordinates make sense only when you know that okay, you're on Earth, and then this is how this whole structure is set up, and then in that structure you have this location. So that's where localization starts. Okay, so you can think of it as like an individual measurement that you generate to say this is the location you are at, but it has to be with respect to something, which is generally the map, and that's why the when you talk about localization, the SLAM thing comes into play, which is the simultaneous localization and mapping, where you kind of build a map along with finding where you are in the map, and then you just keep going. As you keep going, your map expands, and then you localize with respect to that. But not always you would do the SLAM thing because once you generated the map, you can actually localize on top of that, which is something that you do when you're having a robot that is just navigating a area that you're familiar on. Like let's say you have a conference floor and you are building a robot that just walks through the conference floor. In that case, you don't have to rebuild the map every time. But if you're doing an exploration robot that is just exploring a different planetary region, then you do not have the map, so you have to build the map along with localizing with respect to the map. So that's kind of the big picture. And localization itself, there are multiple things in that. Like so, um, you basically look at the different information that's coming in, and you kind of fuse them together and build your location or kind of figure out where you are. So that fusing part, like where you combine them all, is kind of the crux of any localization system, and it's called sensor fusion. And it involves a bit of math, but that's basically the what does the trick. So in a typical robot, you could just have if you're operating outdoors, you will have a GPS and an IMU. If you're operating indoors, we'll have maybe GPS and LiDAR or camera. Sorry, not GPS, the IMU and LiDAR and camera, and then you would localize based off of that. So essentially, what it means is you kind of figure out you kind of perceive what the environment is, and then you build landmarks, and then you localize with respect to the landmarks. So that's kind of like the typical way you would do that. Um, if you're using a GPS, that's a different story because it's kind of a global kind of information, and you don't need to have anything to localize on. So I'll talk about that in a bit. The fusing part, the fusing of information, that basically happens by a mathematical tool called Kalman Filter, which I'm not sure, like maybe some of you guys might be aware of. So Kalman filter specifically tries to put in different sensor information to get a prediction or to get a measurement output. So so just a little bit of history about that. Like this Kalman filter is just was just invented in the 1960s, and this was primarily they were actually looking for a way to fuse all this sensor data for the Apollo missions, and where they went to the moon. And this is basically for the lander to find a spot where it can land. And they were breaking their head over like, okay, what can they do? How can they bring in all the sensor data to get a unified measurement that they can use to predict the position of the lander. And that's when this mathematical tool was brought in, and then they kind of like figured out how to calculate it. So that's kind of like the historical background of that. So what a Kalman filter does, it's essentially on a very high crude level, you can think of it as an averaging algorithm. It just takes data and then it averages it out. So that's kind of like the high level. So you can think of it as an averaging filter. Um, but it's a little bit more complicated than that. And what it does in the background is it calculates confidences or what do you call the covariance, which is basically says how confident I am of this measurement. So for example, if you have an IMU, the IMU will have a lot of noise. So you cannot just say that, okay, I'm 100% confident on the data that's coming from the IMU. Whereas if you're looking at the wheel odometry, which is basically counting the ticks or the wheel movement, then you can say that, oh, I have higher confidence on this. So provide more weightage to that sensor data that's coming in. So basically, it will increase the covariance, the confidence on that, basically decrease the covariance. And then, so basically, Kalman filter incorporates this confidence information into the math and says that, okay, this is how much you should weigh this sensor, and this is how much you should weigh this sensor, and then it calculates the position based off of that. So it also updates its covariance as it goes. So basically, when you say that you can start with some covariance, and then if it changes during the run, or if you had it estimated incorrectly, the Kalman filter has the capability of updating it as you go. So you will, like after a certain run, you can look at the covariance and see, oh, this is how much we are confident about this sensor data. So you can get that information as well. So, so that's kind of like the high level bit of a Kalman filter. And then there is also things like EKF, which is an extended Kalman filter, and an uncentered Kalman filter. These are basically um, uh, the same kind of idea, but it's kind of predicting an non-linear function. So by non-linear, what I mean is anything that is um, that does not change in a linear fashion. Okay, so that's kind of a circle definition. So by so let's say you are measuring the so if you have like a measuring things on a straight line, or like a slope, that's kind of a linear thing. So once you know what where your point is on a slope, then you can say that, okay, where the next point will be on the slope, or the line, if you know the slope, right? So that's kind of like a linear kind of progression. A non-linear thing is where you can think of it as like a quadratic or a cubic curve, where things don't respect a line. It's kind of like using some kind of a non-linear, which is like it's not a line. I guess the name itself says, right? It's not linear. That's not linear. Anything that's quadratic or cubic or polynomial, that's a nonlinear function. So when you get into that, the math gets a little bit more complicated, and that's why you use something called an extended Kalman filter, which uses approximations to get to the nonlinear function. And typically, when you're operating using Kalman filter for localization, it is going to be nonlinear or a EKF, and not like a regular Kalman filter, primarily because any kind of estimation of orientation it's nonlinear function. So when you have orientation in the pictures, then you have to use EKF. Um, yeah, so that's kind of like the basic thing, and that's what they used early on in the 80s and 90s for robots for localization. And then now there are much more advanced methods. One method which was introduced like 10 years ago, which is called graph optimization, where you kind of like represent each of your robot poses as a point in a graph, and you kind of um, estimate the like as you get more measurements, you would refine your poses going backward. So let me try to clarify that. So in a Kalman filter, you estimate a position, and then you move forward, get a new measurement, and you estimate a new position, and then you move forward. every time you do this estimation, you're kind of like baking in some error into it, right? Like whenever you estimate, there could be sensor noise. It could be like um, the non-linearity itself would introduce some noise. As I said, EKF basically uses um, um, some approximations. So when you're doing these approximations, you're basically incorporating or missing out the some of the real measurements. So there is a little bit of noise that comes with that. So every measurement that you make and as you go on, each measurement will have an error to it. And then once you've gone past a certain distance, you would see that you have drifted off from the original location, right? Like that's it's called position drift or orientation drift. And it's kind of inevitable in using a Kalman filter. And there is no way of going and correcting it because your your measurements are baked in and your estimates are kind of like rigid. You cannot say, okay, now I have drift, I can go back and correct that. So the factor graph optimization method kind of um, uses that, I mean, takes that idea and says that, okay, instead of just baking in every pose, I would just keep it malleable in the sense that you'll estimate the pose, but then you also keep track of all the poses that you have generated. So when you go back, like let's say you do a loop closure, you come back and observe the same thing again where you started, then you know that, okay, the current position says I'm here, but I should be somewhere else. Let me see if I can draw something. Hold on. Okay. So let's say you started somewhere here, and then you just went, just drew in a kind of a circle, and then you just came back to the starting location, right? So your position estimate might have drifted, and it would have like when you started it will be in the location, and then as you go it might have drifted off from your location, and then it would have like when you come back to this original initial location, it might say that, okay, you are off from the original location. So this is generally what we call as position drift. And when that happens, you can say that, okay, um, in a Kalman filter, there is nothing you can do to correct this. In a post graph, what you can do is basically what happens is you would let me mark. So each measurement you would do, there is a you get a pose. So basically, it is you kind of like calculate poses at each step. So I'm just drawing some points here, saying that, okay, these are the poses, and like throughout the trajectory. So you can go back and say that, okay, this position or pose is equivalent to this. So there is error accumulated over this whole trajectory. So let's go and correct that. So basically redistribute the error so that it this error kind of like you move this pose to this point. And when you do that and you say that, okay, these are all have some error, then you get a trajectory that is pretty close to what the initial trajectory is. I mean, theoretically, it should be identical to the original trajectory, but practically it's not, but it'll be pretty close to the original trajectory. So that's where the post graph kind of comes into play, where you say that, okay, I can go and update the previous poses. And this was not possible maybe like 30, 40 years ago, because this takes a lot of computing, because you need to keep track of all the poses and all the measurements, and then correcting it, going back and correcting it would take a lot of computing. But with recent computing developments, and also with a lot of updates and like efficiency improvements in math. So for example, even the post graph, um, if you look at the math that is involved, if you're just using storing the poses and trying to recorrect them, it would be like it would take a lot of effort. But what they discovered in the latest like 10 years is they said, okay, there is a certain way you can add these poses such that the matrix is more sparser. And basically what you need to do is when you're doing this correction, you have to invert a matrix. And the number of poses in the matrix would mean the number of rows and columns. So let's say you have 10 poses, you have a 10 by 10 matrix. Inverting a 10 by 10 matrix is a lot more work than inverting a 3 by 3 matrix. Now imagine that if you are having a trajectory that is, let's say, a few hundred meters long, and then you might have like a few thousand poses in them. So let's say even 1,000 by 1,000 matrix. If you're just trying to invert 1,000 by 1,000 matrix, it is, I think matrix inversion is cubic, like order of 3, um, like order of n cube. So that would be like a lot of compute cycles that you cannot even imagine you'll need for that. So what they kind of figured out is there is a certain way in which you can set up this graph that such that it is a sparse matrix. A sparse matrix is basically a matrix that has elements primarily along the diagonal. So if you have a sparse matrix, then inverting that is pretty simple. It's kind of a linear operation. What they figured out is like if you can add these poses in a certain way, and you can change the graph in a certain way, you can keep the matrix sparse, and then you can use that to do the inversion. Um, so so both the computing advancements, but also the hacks or the tricks that we have figured out in linear algebra actually helped to kind of do things like that. So that's where this postgraph thing comes in, and that's like a lot of most of the robots nowadays just does this. But that being said, there are still a whole bunch of robots that still do Kalman filtering and EKF, and because it is simple. You can do it on an embedded processor. You don't need like fancy computer to do that. And it's kind of constant time because you're just dealing with one post at a time. You don't have to go back and correct the things in the past. So it's very much suited for like embedded systems. So a lot of systems still use that. So I guess that's a long-winded answer to kind of like giving you the brief uh, terrain of what position or localization is. I can go
Yes.
into details, or if you have any specific questions, I can answer that.
So you were referring to the term covariance when
Hmm.
explaining Kalman filter. So I
Hmm.
did not understand that part. Like what
Uh,
exactly were you referring to as covariance?
so covariance is basically it's a square matrix which tries to encode what um, the let me try to explain how to. Okay, so let's just draw something, see if we can answer that. So so let's say this is not a square. Oh, yeah. Let's say this is a square, and let's just draw some. Okay, it's a very bad square, but bear with me here. Okay, so so I said it's a square matrix, and then you have entries. So let's say um, you have x, y. So you're let's say these are the variables you're trying to track. So x, y, z, and okay, I want to move this. Okay. So typically what you do is uh, in any kind of like a simple system that is operating on a ground, like uh, which does not have to, oops, which doesn't have to be flying or anything like that, like a drone, you would just use the xy, and wait, actually it's not even z, so it's just xy and theta. So these are the three variables that you would use um, to um, to kind of track any system that's operating on the ground. This basically makes it simple. But what I mean by that is like you're looking at so think of it like a 2D graph, like on paper. You have this X and Y axis, and then you're also tracking the theta, which is the yaw radius, like how like the which way you're facing. So on a ground robot, this is generally what all you need. But whereas on a if you're doing a drone or something like that, then you would track your six staff pose, which is like XYZ and the roll pitch yaw. There is also other things you track like the velocities and things like that. So let's keep it simple. Just say we are tracking the X, Y, and theta. And in so when I say covariance, what I'm referring to is like if you look at the term itself, it's covariance. It's basically like the variance of a particular kind of like a variable, like how it is different with respect to something else. So when I say, I mean, typically you would, I mean, this is kind of like drawing the covariance matrix for the output, but it's typically the input that you'd use. So if you're using wheel odometry, and the X and Y would be like the X and Y change in the wheel odometry. So let's say your robot is X forward, and in that case, you're just driving forward with the X in a if it's not an omnidirectional robot, which means that it can move in any direction. If it's a regular kind of like a four-wheeled robot, then you're generally moving in the X direction if it's X forward, and your lateral or Y direction is not. You generally don't move in that direction. Um, what I mean by that is, let's see. I guess I'm adding a lot more complexity here. Oh, shit. Okay. So let's say that you have a robot that has four wheels. And so if your robot is um, just an Ackerman steering or like a differential drive. You have the robot driving in this direction, but the robot will not be moving in this direction, right? Because the wheels are facing this way, so it has to be this way. So that's what I mean by like moving in the X direction. So if your robot is X forward, your Y would be this and Z is pointing up, then then your X would be changing, but not the Y. So anyway, um, so what I mean by the covariance is you're saying that, okay, this is a covariance matrix. You have X, Y. Here you're saying like how much of the, like what is the variance of X with respect to X? What is the variance of X with respect to Y, and X with respect to theta? Um, so I guess maybe I kind of like, it might be better if I talk about sensor data instead of X and Y. Okay, so let's see. So, okay, if we are, so in the odometry data that you get, you can say that your X changes with respect, like, okay. I'm just wondering which is the best way to kind of like lay this out so that it is easy to understand. Um, so So one thing that kind of like happens in these kind of systems is like your theta, your angle variation. You don't have much confidence in that with respect, like compared to your changes in X or Y. So when you're filling in a covariance matrix, you generally start with the diagonal elements, which are easier to understand. What is your confidence in your X, Y, and Z value, or X, Y, and theta value? So let's just go ahead and write some values here. So since our robot is X forward, and we know that or we kind of believe that the wheel odometry is like really good, let's say our covariance here is maybe like 10. And then a covariance along y is also generally good because we are not expecting to slip a lot, and whatever the odometry is giving, we assume that the y value is also not changing that much. So we'll just say 10 for that as well. Whereas if we think about the theta value, that is coming from the IMU, and we would expect some more noise in it. So we would say something like 100, basically saying that it's 10 times more than the covariance along the x and y. So this is kind of like how you would do. And typically what you do is you just fill in the rest of this with zeros, and say, okay, that's it. That's the covariance matrix we start with. As the robot progresses, there might be some errors, some errors that it can pick up, and it can fill in some of these values, but typically it stays diagonal. But if you're when you say that like what is the y with respect to theta, that is basically whenever I get a y measurement, how much like confidence that it would contribute to the theta value. That's what you're saying there. So it's not intuitive, and that's why I'm finding it hard to kind of explain this. But essentially, you get this idea of the numbers that you put in here, right? So it's a unitless number, unitless matrix. So the actual absolute values doesn't make sense. It's just like comparatively how these are set up. So in fact, you can go ahead and say that this is one, and then this is 10. That should also work because you're just saying that it's comparatively how it's changing with respect to the other values. And there is a matrix that is related to this, which is called an information matrix, which basically um, is kind of the inverse of this. It tell you like you tell like what is your confidence instead of the covariance. So it'll be like in that case you'll have more value for the x, y, but less value for the theta. But typically for the Kalman filter math, you use a covariance matrix. So that's what it is. I know I didn't explain it properly, but I know, did it answer your question?
Yes, I got an idea about this.
Okay. So in any kind of system, tuning the coherence matrix is kind of a big deal. And if you set up the value, so one thing you could think of is like, okay, let me set up a really big value, and and then hopefully the filter would converge and figure out the values itself. That doesn't happen. So if you do that, your covariance matrix will blow up. And blow up in the sense like all the values will be higher, and your position estimate will be like um, completely like you don't know, you will not know what your position estimation is. So you have to, and you cannot set it too like too low, or like you cannot set the confidence too high. When you do that, then you're kind of like giving conflicting measurements, right? So the way you can think of it is like, let's say, so if when you say that this is the right position estimate, and you're getting measurements. So let me see if I can draw this. So let's say this is your position, the true position estimate, and then let's say you get a measurement that is um, one sensor says you're like, if you use that sensor data alone, it might say that your position is here. And then if you get another sensor measurement that it says the position is here, but your actual position, if it is the actual position is probably here on this trajectory. So if you set the confidence on this sensor to be like very low, and if you set the confidence on this sensor to be a little bit higher than that guy, then it makes sense for the Kalman filter to say that, okay, I don't trust this much, so it can be a little further away, and this is I trust this much, so the trajectory will be somewhere here. So that's convergence. But if you set the inverse, you said that I have a lot of confidence on this sensor, but a lot less on this sensor, then your position estimate would be somewhere here, right? Because it's closer to that. And then your trajectory would be like out of the way, and that's when I say like the things would blow up because it wouldn't align. Because when this guy, the next time this guy comes in, it'll be somewhere around maybe here, like it's just jumping around, right? So it might say somewhere here, but this guy might still say that, um, okay, we are still here. So now your Kalman filter is confused. Like, okay, I was here, and then I just got a small update, but this guy says here, I cannot jump all the way here. So your Kalman filter gets confused. So you have to give some realistic measurement on what the covariance is. And you typically get that value from the manufacturer itself. Like, for example, if you're using an IMU, the manufacturer itself would tell you what the covariance is for each of these axes are, and then you start from that and refine that as you go. Okay,
Yes, I got it.
cool. Okay, so that's a very long answer to a simple thing, but it's actually a really important kind of area in robotics. So it's good to understand. And the things that I told you, if you actually look at, like, go back and look at it, I didn't explain any math, right? I didn't write any equations. I just gave you an intuitive understanding of what's going on in the background, which is kind of important to understand initially before you actually jump into the math. Because once you jump into the math, it gets like you'll have no idea like where it's going, why are we doing that. So these are things I kind of picked up over these years, and I feel that's what is going to be useful. And then once you know these basics, like the underlying principles, then if you go back and look at the math, it becomes a lot more easier to make sense of what's going on. Okay, cool. So you guys have any other questions related to this, or complete different
So
domain? Yeah, go ahead.
uh, I've got one question. Like
Mm-hmm.
you've said that we are taking in sensor data. So how this covariance matrix is going to change if more sensors are looking for the same data? Like
Most sensors are looking at what?
like more. It, here we took that two sensors are there,
Mm-hmm.
maybe GPS and ODOM or
Mm-hmm.
IMU.
Mm-hmm.
So if some more sensor comes into picture, so how
Mm-hmm.
this matrix gonna change?
Basically, the matrix size increases, right? As I said, I started with 4 and then is restricted to 3 by 3. But typically, if you have um, a lot more sensors, so typically what you do is you kind of like track um, the variables that you're. I'm trying to recollect, like uh, uh, part of it is
So like
hey,
does the
sorry.
matrix dimension increases?
Yes, that
Like
is true. That's what I'm saying. But I'm just wondering, like, what I'm trying to recollect is, um, I do know that you would track the variables that you're estimating. So for example, what I mean by that is like when your sensors is going to give you some information. So for example, your wheel encoders would give you the wheel text, right? Like how many tick. So basically, a wheel encoder would count the ticks that have progressed. So they have these markings, and then as the wheel moves, you would measure like how many ticks have kind of um, passed through. So that's how you measure like how much you have moved forward. So that's a wheel encoder, and then an IMU is going to give you the roll pitch yaw and sorry, no, it's not going to give you roll pitch. Yeah, I'm use basically two devices. It's a gyroscope and an accelerometer. A gyroscope would give you angular rates. It's basically telling you what's the rate at which you're turning, and an accelerometer would give you the acceleration along the three axes. So basically, the way you should think about it is like um, you have the 6 degrees of freedom, the X, Y, and Z, and then the roll, pitch, and yaw, right? So X, Y, Z is basically in 3D world, the X location, the Y location, and Z location, like where you are, the point in 3D space. And then the roll, pitch, and yaw is like how, which angle you're facing in that point. So if you just have a 3D point, you just say X, Y, Z. And then if you assign a direction to that point, then you have the roll, pitch, and yaw. So that's basically a 6 off pose, or like 6 degrees of freedom represents a 3D point with a direction facing in 3D world. So your IMU, when we say it's giving you um, the linear acceleration, what we're talking about is the acceleration, which is the second order value for that position. Like if it changes position, you would know that. Okay, I'm going to a lot of physics now. So okay, so you have a point, and then your point moves to the next to a different location, right? So now you call this displacement, right? You have a point in X, Y, Z, you have the point moving to X dash, Y dash, and Z dash, then you know that it's a new position. So maybe let's draw that. So uh, this is, oh, my pencil is, what's going on? Okay. So let's say this is your X, Y, Z. And then let's say you move to a different location. And this is X dash, Y dash, and Z dash, something like that, right? So this is displacement. And then when you look at the rate in which you're changing, like how fast you're going, that is speed. So that is with respect to time, right? You're saying like, okay, I move from this point to this point, and this is my speed. And then when you look at the rate of change of that speed, that is acceleration. So it's basically the you're adding time to it, and basically you're measuring the rate of change. So if you're just measuring the rate of change of your displacement, that is speed. If you're measuring the rate of change of your speed itself, that is acceleration. What your accelerometer gives from the IMU is the rate of change of your speed. So it's to get the displacement, you have to uh, differentiate that value twice. And that is really noisy. Again, I'm going into too much details on these things. Probably I should lay a foundation before I get into these.
Ah,
Anyway,
sorry, it will be integration, right?
is it integration? Did I mess it up? Uh,
Yeah,
I think, yeah, right. Okay.
second
Yes, yes,
derivative of
yeah.
position is going to be
I
acceleration,
kind of
and
messed up. Yep. Okay. So basically when you double integrate things, it kind of like messes things up, right? Um, so that's kind of like that's what your kind of like IMU gives. And then it also gives you the rate of change of your orientation. Like that's like one thing down. It's not like twice as much as the the acceleration. Anyway, so these are not giving you the values that you care about, right? Like a Kalman filter is trying to estimate your position and orientation, maybe the velocity as well. And um, whatever the IMU is giving is not the position or orientation per se. It is giving you uh, um, the the time variant of that, right? So what generally happens is you would have these matrix that this is the part I'm kind of like I need to go back and look at the details. It's been a while since I worked on this Kalman filter, but I believe keep the covariance matrix for the measurements that you're or for the values that you're kind of estimating. So basically the XYZ, the velocities, and the position. Um, and then say like how much the accelerometer values um, would contribute to these values that you're measuring. So So that's generally what happens. So the robot localization package in ROS, which is kind of like now most people generally use that. They don't generally write Kalman filters from scratch because it kind of tracks the position, the XYZ, the angles, the roll pitch yaw, and also the velocities. So I think it tracks like 15 variables, and and it's also like a well-written Kalman filter and tested well enough. So if you're starting with ROS and you're just setting up localization, you would probably use that package. So that basically tracks like 15 variables. Um, and I kind of lost my thought on what why I was going there, but yeah. Have any of you guys used the robot localization package? No. Okay.
No.
Yeah. So once you do localization, I think that's and if you're using ROS, that is one thing that you would generally start with, because you can play with the you can play with with these different values and the sensor data and figure out how it's operating. You don't have to like write the filter from scratch. So it's kind of like an easy thing. So Shreya, you asked about localization. Like, are you working on localization now, or like, what's the motivation there?
No, sir, I will work on localization the next month in December.
I see.
So that's the reason why, yes.
Okay, cool. Cool. Yeah, so just talking here, I kind of realize I need to brush up a few things on myself as well. I need to go back and look at these things. It's been a while since I worked in like hardcore localization. Like when I joined CMU, and the next couple of years, we were just building these kind of systems, and yeah, I've moved on from those, but I should go back and refresh myself. Cool. So sometimes, like, just give you an anecdotal kind of thing. We used to like for one of the projects, like we were trying to automate an ATV. It's ATV is an all-terrain vehicle that can you see it in movies where you can just drive through like forest and things like that. So and we were thinking of like really complex ways of localization. We were using lidar cameras and postgraph and everything. It just turned out that if you use the vehicle, the wheel odometry and GPS and IMU, that produced good enough localization comparable to the other methods that we used at that time. So what I'm saying here is like if you have sensors that are giving you really good data, you don't have to need really complex methods. You can just use like simple Kalman filter, basically an EKF to get the position. So that's what we ended up using, just the GPS and the wheel odometry because that was really good. So that's something that you have to keep in mind when you're kind of designing these systems. Like, is there an easy way to solve it, which we generally overlook? Okay, cool.
Yes,
And
sir.
so,
So I have one question.
go ahead.
If so I've built manual robots, but I
Uh-huh.
have done and I've done simulation, but I haven't deployed autonomy on real hardware.
Okay,
So if I want to start it from, and my 6 month internship is related to that only. So
okay.
if you want to start applying autonomy on real hardware, so where should I start from?
Um, Actual hardware. So the thing with robotics is like, I mean, you could start with um, simple systems, but the thing is like you can. So you said you're in an internship, right? Do they have like real
So
robots there?
yeah, so sir, I implemented one robot, but
Okay,
that is on Green Guardian robot related to planting, watering, and that.
okay.
So I have to make it autonomous in my 6 month internship starting from January.
I see. Okay. So
Yeah.
yeah, I mean, that's if you have that hardware, I would say start from that.
Okay. So basically, first should I start from simulation of the
Uh,
real hardware and
that is typically easier. Um, yeah, and it depends on like the hardware itself and like so there's a lot of
okay.
details there. So to start with, if you have if you're using a robot that is already well established, then you might have a simulation for that already available. By simulation, what I mean is like a URDF file that you can load to Gazebo and you can just simulate it there directly.
Yes, sir.
But if not, then you might have to develop those, and that might mean a lot more work than actual working on the actual hardware itself. So yeah, it depends on the robot and the problem that you're dealing with. So typically what we do is like depending on the time, right? So we were building a robot. I don't know if you guys are familiar with Zoe, which is kind of um, a planetary rover which has this huge solar panel that we take to the deserts to test it, to drive and also do some science. We're building a second version of that, um, and when we started, we went ahead and tried to build a replica of that in a simulator. It took us a long time, but it actually paid off because the development took some time and was delayed due to like some other things like the mechanical stuff was not coming together, and we ran into some issues with manufacturing and things like that. But essentially, what happened was we had this 1 week window where the hardware was ready to be tested, and then the software had to be ready to kind of like be on the hardware to actually drive the robot. And in a typical setup, 1 week is not sufficient. Once the hardware becomes ready, you write the software, you set it up, and all those things. It takes a couple of weeks to a month to get the robot up and running. But in this case, since we have everything replicated in simulation, when the hardware became ready, we just transitioned the simulation software to the real hardware, and it just worked out of the box. There's still very few things that need to be fixed, but it within a week we were able to get it up and running, which is kind of really impressive when you look at these kind of systems. So, but then there is also the sunken cost. Like we spend a lot of weeks and months trying to set up the simulation beforehand. So it doesn't. It's not free. There is some effort that you need to put in to get the simulation up and running. But if you can get that soon enough, then it is much easier and faster to develop in simulation and then transition to the hardware. I I hope it answers your questions. Did it?
Yeah. Yes, sir. Yeah. Thank you,
Okay,
sir.
cool. Okay, I think we're at the top of the hour. So if there aren't any final questions, I think we can log off. Anything else? Cool. Thanks for joining. Um, and I guess you guys are asking really good questions. So come up with more questions. If it'll be really helpful for both you and me if you send me the questions beforehand, so that maybe I can bring in some other things like maybe some graphs or uh, prepare something that would be useful. Okay.
So next session we are going to discuss ROS 2, right?
Yes, that's the plan.
Okay.
Okay. So how many of you are familiar with ROS2?
Yes, sir.
Briefly, not in depth.
Sorry. Okay. Okay.
I have
Uh,
worked, sir, with Ross
yeah.
too.
Okay.
So,
Like,
would you recommend anything like for us to go through
I,
to make
I
good use of the upcoming session?
I guess, like, can one of you talk? Sorry, I couldn't get what you
Yeah.
said.
I was asking, would you recommend us going through any resources beforehand to make good use of the upcoming session?
Uh, Maybe, I don't know. So let me think. Um, Probably. So yeah, let's say go through ROS 2 a little bit, see what you can kind of like uncover in that, and then maybe you can go in depth. So it's not going to be like a uh, uh, like I'm going to go through on a high level, like what ROS 2 is, what are the things that you can do with it, like how things are structured and things like that. So if you already worked in ROS2, then probably you don't have to do much. But if you don't know what ROS2 is, then maybe just a little bit trying to understand what it is, and then we can go in detail in the session. Okay.
Sure, sir. Sure.
Okay. Cool. I think someone else was speaking. Was this Krishna or Rhythm?
No, sir, I was saying that I have implemented in 2 to 3 robots, ROS 2.
Nice. That's
Yeah,
cool. That's cool. So maybe you can jump in during the discussion next week
sure,
on
sir.
that. Okay, cool. That's good. Okay.
Thank
Nice
Yes,
talking to
sir.
you guys. Talk to you next week. See you.
Thank you, sir.
Sure.
Thank you,
Thank
and
you.
bye bye, guys.
Yeah.